In this video lecture, we have a first look at high-dimensional statistics. In particular, I will explain what the problem is in high dimensions, why we need to address that, and give an outlook at how we are going to tackle this problem in this course. First, let me explain a bit the general notation and setup that we will use. So these slides will also be available separately, so that you can always easily access them as a reference point. So general notation, I use small letters for scalars. I use boldface for vectors, and I use capital boldface for matrices. We generally assume that we observe pairs of data, yi, the dependent variable that we want to explain, that we want to predict, for instance, and xi, the regressors, the covariates, or if you want to give them a more machine learning name, the features that we have that help us to explain why. We usually index observations with I running from 1 up to n, where n is our sample size. X we assume to be p-dimensional, so we have p different regressors that we use to model y. High dimensionality will come from the fact that p is going to be large. If we look at the general model, without making any particular assumptions, we assume that there is some function f of x which is going to generate y. There's also going to be some error term. This relation is not going to be exact. So there's going to be some error term epsilon I, which we can also call innovation. So just to clarify, when I write things in matrix or vector notation, I denote boldface y as the vector of all observations of the dependent variable, so y1 up to yn. I denote capital boldface x to denote the matrix of all explanatory variables, where every column in x represents one explanatory variable, so all observations from one explanatory variable. The same goes for boldface epsilon, that is the vector of all error terms. So what we will mostly be focusing on is the linear model. So here the function f from this slide is going to be just linear, and there is going to be a parameter vector beta, which in the end is the object going to be of our interest. Right? We don't know the values of these betas, and those are the ones we are after. Again, and we can write it in matrix form, which will often be easier to work with, as here on the right hand side. Now, even though much of what we do is in the linear model, there are a number of things that we can say about this. First, we don't necessarily believe that the true models are linear, but there are many reasons why we still want to estimate linear models. Of course, a linear model can be seen as an approximation to a more complicated nonlinear underlying model. And in fact, if we want to improve that approximation, high dimensionality will come in. So in high dimensional settings, it actually makes sense to consider linear models. We will come back to that later on during the course. Now, there are a bunch of extensions which easily fit in. For instance, you might wonder, well, I want to do some sort of time series modeling, maybe VAR modeling or whatever. Well, you can obviously include lags of your dependent variable in your regressor matrix. You can also allow for serial dependence wherever you need it. And we can also allow to have multivariate regressions, where we actually don't observe a scalar yi, but we observe a vector, such as we would when we do VAR modeling. There are some notes on Canvas where we show explicitly how you can actually do, for instance, panel data models and VAR models, how you can write them in a standard linear regression framework. So all of what I explain here is equally valid to for those cases as well. And moreover, in fact, the problem of high dimensionality occurs in whatever model we have, where we have p, the number of parameters, large relative to n, the sample size. So by focusing on the linear model, which is the simplest one, of course, we can still illustrate all the problems and also all the solutions without having to go into complications of estimating nonlinear models. Now, obviously, you can all of these things transfer to more complicated settings. And to illustrate that, let me just consider one nonlinear model, which we'll sometimes also refer to, which is the binary classification model, where what we observe as dependent variables is a vector of ones and zeros, or at least it can be coded as a vector of ones and zeros, where something happens or it doesn't happen, essentially. We have two categories that we observe as outcomes. And we would still formulate a linear relation among the x's, but then of course to translate it to y, we have a nonlinear relation. So typically the way we do it is we say, well, if beta prime xi plus epsilon I is larger than 0, we end up with a 1 for yi. If not, we end up with a 0. Now this threshold of 0 is arbitrary because we can of course include a constant in our x, which means you can always put this threshold to 0. Now what we typically do in econometrics is we extend that model by saying, well, what we have is some sort of, so we call a latent variable, a yi star, which we actually do not observe. It's a variable that is actually the where we can fit the linear model on, and based on the outcome of that latent variable, we either observe a 1 or a 0, depending on whether the latent variable is larger or smaller than 0. So one particular example where we give a meaning to that latent variable is, for instance, in we call econometrics and discrete choice models, where you look, for instance, at the customer deciding to buy a product or not, where this linear part would indicate his utility. So there are features of that product, and if he's happy enough, if he likes the product enough, so if his utility for this product is high enough, larger than 0, he will decide to buy it. Otherwise, he will decide not to buy it or buy an alternative product. The way we approach this problem typically in estimation is we look at a certain distribution. So we formulate a distribution for our error terms, and then of course we can derive the probability that we observe a 1 conditional on our axis, which by simply rewriting the condition to observe a 1 ends up with simply putting beta prime xi into f. And this will typically be the object here that we are interested in. But still, we need to estimate the betas. So we do in econometrics. There are of course alternative ways to do it, but we do in econometrics. We assume a particular distribution for f, and we do maximum likelihood. Right. Take the normal distribution for f, you get the probit model. Take the logistic, and you get the logit model. Or if you want to not to call it, give it its econometric name, but its statistics name, we call it logistic regression here. And of course, we can actually generalize this setup by focusing instead of distributions on link functions, where we say that if we transform the conditional expectation of y given x in an appropriate way using g, we get a linear function. So what we've basically been working with on the slide here is that we are doing then the inverse of that g. And depending on the form of link function, you get a specific model that you can estimate. And of course, these link functions match to particular distributions. Crucially, no matter what kind of model we use, we always need to estimate these betas. And if the dimension of them, p, is very large, you have the same high dimensional problems as in the linear model, where the g function is just the identity function. Which is why we will mostly focus on the linear model, on what is coming. But do note that everything is extendable to all sorts of other models as well. So finally, what are we going to do with these betas? Well, there are two things we could be interested in. The first is we could want to do inference on the betas. So we want to learn about the betas. One very common question would be, well, which of these betas are zero or which betas are non-zero? So you can determine which variables are irrelevant and which ones are relevant. Following up on that, we can test for particular values. So we do hypothesis tests on the betas. If we test, of course, we can test whether the elements are zero, so we're back in the first case, but there also might be other values that you might want to test for. We can also construct confidence intervals for elements of that. And of course, we could not look just at the elements themselves, but we could also look at certain functions of these elements. The other thing we want to do is prediction, and the reason to split the two is actually that here the values of the betas themselves do not really matter. Well, what we want to do is, suppose we have some sort of new observation, let's say that the n+1 observation of x. We want to give a prediction for the corresponding y. Now, of course, if we want to give a prediction, we need to have estimates of beta because we can use those to construct a prediction. But the betas in themselves are not of importance. And in fact, you could basically argue that even if you would have completely the wrong betas, but you get the same prediction, it's the same outcome there. Now, prediction should not just be seen in the classical econometric way of forecasting, right? Think macroeconomics or finance. Forecasting will happen in the future given the past. But it's also things like classifying an email as spam or not is equally well a prediction exercise, right? We get a new email with new features in X, certain characteristics of that email, and we want to find out, well, should we have a 1 for spam or a 0 for non-spam, based on the emails that the algorithm already analyzed before. Same as making recommendations to customers. If Netflix shows you which series or movies you should watch next, that is also a prediction problem. Now here we can distinguish, of course, between point predictions, getting single values, or predictions which take into account uncertainty, which would be then either interval or density predictions. And one final concept that we would make a distinction on is out of sample versus in sample prediction. So out of sample is really, as we done it here above, where you say, okay, I have new information that I did not use before, and I want to get a corresponding prediction. But you can also do it in sample, saying how well can we actually fit the values of y. And well, this is something we're going to make some distinctions on about as well. Well, that sets the stage for the kind of settings that we're going to consider. So let me now go into the so-called curse of dimensionality and the reason why we actually do high dimensional statistics. So for illustration, take our linear regression model and assume that P is relatively large. In that case, we call it high dimensional. We will see later what it actually means relatively large compared to n. What is the key feature is that we have a situation where we don't have essentially enough observations to estimate this model in a standard way. Right, so in the case of the linear model, you would want to use ordinary least squares, for instance. What we will see is that if P gets large, this will break down. Because these methods are not designed to handle such settings, they're designed to handle settings where P is relatively small, where you have enough information you can actually estimate the parameters. So what I'm going to look at here in this lecture is what is going to happen if we apply standard methods to a high-dimensional problem. And there are two things which are going to happen, which are going to be high variance and overfitting. And this problem, the problem of having not enough information and being not large enough to estimate all p parameters, that is what we call the curse of dimensionality. So one crucial concept for analyzing this is the mean squared error. Remember, the mean squared error is a measure of how well are we estimating the true parameters. So if beta is a vector of true parameters, beta hat is our estimator, we're looking at, if it would be just scalars, then it would just be the expectation of the squared distance. If it's a vector, we look at a norm. I'll come back to these norms later. If we write it out, I'm not going to go through all the steps here. They're fairly standard. You may also just want to, if you don't want to check, you just believe it. But what we get here is the familiar formula that mean squared error, which we then use as a measure of accuracy of our estimator beta hat, is the trace of the variance covariance matrix plus the inner product of the biases, which in this familiar form for a single estimator is just variance plus bias squared. So an estimator accuracy can be described in terms of its variance and its squared bias. And now what standard estimation methods in general do is, well, bias we want to have very, very small. Not necessarily unbiased, but at least very small. So we minimize this, and then given that for all estimators that have this small or equal to 0, we try to minimize the variance. And so we end up with situations in high dimensions, as I will show later, where we have unbiased estimators, but because they insist on being unbiased, their variance is going to be very, very large. And so there is this trade-off between variance and bias, and standard methods basically go for minimizing bias first at the expense of having higher variance, which fails in high dimensions. And as we will see later, what we therefore basically are doing in many high dimensional estimators is allowing for bias, which will allow us to reduce variance. Now we can do the same thing for predictors. So here we don't have to make a distinction between whether we do parameter estimation or prediction. So here it's again written out. We know that theoretically our next observation, yn plus 1, is going to be beta prime xn plus 1 plus, of course, an error term. Well, we can estimate beta, so our prediction would look beta hat times xn plus 1. So what is the mean squared error of that? Again, we just look at the deviation between yn plus 1 hat and yn plus 1. We can write things out. Again, I'm not going to go through all the steps. What is important here is, again, we end up with the result that M is E. So the accuracy of your prediction is going to be the variance of your prediction plus the squared bias. And here plus the variance of the error term. So this makes sense here because we know that the true prediction, of course, is something which depends on a random outcome here in f epsilon n plus 1. But we cannot control that, right? This is basically just how accurate is your model. It has to deal with signal to noise ratio. So this part we cannot control, it's just there. But these we can control. And these are, again, we have exactly the same issues here as for estimation of beta directly. So let's see what happens if we have a high dimensional model and we do least squares. Right. Least squares is, of course, our most basic estimation method. what are we going to do? We're going to take the sum of squares, square differences between y and the fitted values, and we're going to minimize that. And of course, if you work it out, you get the familiar formula for least squares, which looks like this. Now, what we usually do when we estimate, when we can evaluate the properties of the least squares estimator, we look at asymptotics. But asymptotics assumes that p is fixed and n goes to infinity. But if p is fixed and n goes to infinity, you will always have enough information in n to estimate these p parameters. So even if you would say p is large, well, if n goes to infinity, n will always be much larger. So asymptotics here does not help us, in the standard way at least, to evaluate what's going to happen in high dimensions. So instead we're going to make some distributional assumptions. So I'm going to assume here that my epsilon has a normal distribution, because then I know that conditional on my data, the only thing that's random is these epsilons, and normality also holds for the least squares estimator. And in fact, I have I can show easily, go back to your statistics course, for instance, to look at this result that has a normal distribution with mean beta and this variance covariance matrix. What we will now see is, because this is an exact result, exact distributional result, we can analyze the properties of this thing, assuming p to be relatively large compared to n. What we're going to see is, well, as you can already imagine, because there's just the beta here, the mean remains beta, and it remains beta also if the dimension becomes large. So least squares will remain unbiased in this setting. The problem is going to be here in the variance. Let's assume the best case where we actually have orthogonality. That means orthogonality means that if you do x prime x divided by n, you end up with the identity matrix. Capital I here indicates the identity matrix of size p. Of course, in this case, if you plug in into the variance expression of the least squares estimator, you'll get something that does not depend on p apart from the dimension here. Now, in general, of course, this is not the case. We usually do not have orthogonality. It's a very strong condition on your regressors. So it depends on, of course, the form of your axis, what will happen. So the best way to illustrate that is doing a little simulation exercise. So what I'm going to do is I'm going to choose a variance covariance matrix of my axis given by sigma. And I'm going to choose it such that, very simple, that the variances are all going to be 1, and each regressor is going to have a correlation of rho with all the other regressors. And I'm going to simulate my y's just as standard normal. So basically, I'm going to simulate a regression model where all the coefficients beta are going to be equal to 0. And then if I do that many times, I can just simply record what the variance is going to be in every for all of these settings. And what I'm going to do is I'm going to let my dimension p, going to let that increase here. So I have n observations, and I'm going to take n equal to 100. And so n is 100, and p is going to increase from 1 up to close to 100. And you see that depending on the values of rho, the variance is going to clearly increase. And interestingly, even if rho is 0, we already get an increase. So you might wonder, does that not contradict to this orthogonality? Don't we have orthogonality? Well, in fact, we don't, right? We have orthogonality maybe in population, but not actually in the axes themselves. But we do just have uncorrelated axes. So even in that really best case, you get a variance which increases And it can increase quite dramatically if you look at the scale here on the y-axis. So if it starts at 1 and it actually goes, if you have a row of 0.6, which is not even that high, when you have 80 variables, you have already more than 20 times the variance. Which means your estimator becomes very unstable. So basically it's going to be all over the place. It remains unbiased, but well, it could be anywhere. And the same we can do for predictions, but actually for predictions the effect is even worse. So we're going to predict our next observation yn+1 using just beta hat prime xn+1. Again, it remains unbiased because the beta hat remains unbiased. But now for the variance, well, we can just write out what the variance is. You end up with this expression here. And now plug in orthogonality. So we have, suppose we have the identity matrix, in which case this part will drop out. And what we have here is then xn+1 prime xn+1. So just the sum of all the xn of all the covariates in this new observation divided by n times sigma squared, which will be approximately proportional to p over n. Right? You have divided by n. So here's a divided by n missing. I will update the slides with the correct formula later. And here we have sum over p, and generally we could assume that, I mean, unless these predictors actually 0, this will all be non-zero. So you have a sum of p positive terms, so this will be roughly of the order p. So here you see that if p is going to increase, then we are in the best case scenario, we have a linear increase of the variance. And that is only, of course, a best case scenario. So let's look again at what happens if we simulate the same model as before, so 100 observations. But now we look at the prediction. Well, you see the same kind of curved lines as you saw in the previous graph. And so that doesn't seem to be different, but if you look at the scale here, it's very different. Right, so here we have a variance which becomes thousands of times larger when we move to having almost as many predictors as we have observations. And of course, we don't go further here than close to 100. I mean, if you go further, you cannot even do OLS anymore. If p is larger than n, then x prime x inverse will not even exist. So you cannot even use the formula to get estimates anymore. But of course, I mean, that will be a problem we're actually going to address as well. So this is even really a case where p is just even small, not even as large as n, and already there we run into massive problems. So let's look at the second problem, which actually is the same problem but expressed in a different way, and that is overfitting. And overfitting simply means that what you do is you're going to really fit the data itself. So rather than actually trying to fit the model part and get rid of the noise part, we're just fitting everything. Now let me illustrate that with a very simple model where we say, okay, yi is some function f of xi, a single covariant, plus some error term. If we know we have such a model and we don't know f, but we know that it's smooth enough, right, to enough derivatives exist, then what we can do is approximate f using a sum of polynomial functions of x. And this just comes from the Taylor expansion. So what we can simply do is we fit a linear model, and we don't fit it just on x, but we fit it on powers of x. And we put x up to the power p in here. So here you already see one case that I mentioned before where we actually have a nonlinear model, but we can approximate it using a linear model. But we also know that to get this approximation accurate, we need to have sufficiently large number p. And in fact, our Taylor expansion tells us that the remainder term gets smaller if p gets larger. So you would want to include quite some values, and you would think that it's actually better to put in a larger p rather than a smaller p. Well, in theory, yes, but in practice, we run into the high dimensional problem. And what happens is the following. So I've taken here the function f to be the sine function of x, which of course is very smooth. You can see it here in blue. This is what the true function looks like. I generate data around that, which are the black dotted line represents the data, and the red line represents the fit of my model. So the first thing I'm going to do is going to just take p equal to 1, which means I'm only going to include a linear term. Of course, I mean, if it's linear, it will always be a straight line, so you cannot do much better than this. I can go quadratic. Well, I still cannot recover the shape. So I get a line like this, which is the best fitting quadratic function, which is still not very good. So clearly I should then put in more terms. Well, for instance, here is a graph for p equal 5, so I put all terms up to order 5, and then you get something which is relatively close to the true function. Well, let's see if we increase it more, what will happen then. Hopefully it will become even closer. But we see if we go to 10 here, for instance, well, we still sort of get the shape, but there are some weird things happening, in particular here at the end and here at the beginning. The line becomes a bit more wiggly, which does not really seem to do a better job. Let's take things more to the extreme, take p equal 50. And you see that the line becomes a lot more wiggly, and we tend to pick up things and places which is really just noise. So it picks up stuff from the data that is noise and actually not really the signal. And for p equal to 99, well, it's all over the place. So you can still roughly see the shape of the original function in there, but it's going everywhere. It's picking up lots of stuff. And it's we are really overfitting the data. And I mean, as you can imagine, what happens, of course, here is really the high variance of the estimators of the coefficients, and it's going to be all over the place. You will not be able to detect that anymore. Predictions will be all off. I mean, look here what happens in the end of the sample. It's really going horribly wrong. And this is typical what we see in high dimensional models. So what should be clear from this point is that we cannot ignore high dimensionality and apply standard methods, even disregarding the fact that standard methods cannot even be applied if your high dimensionality becomes larger. Take a setting where p is larger than n, least squares will not work anymore. So we want to address this high dimensionality. Well, the first thing to realize is that it does not come for free. If you could simply do it for free, well, then there would actually not be any problem, right? Why would we even care about it? So we're going to have to make some concessions. And the type of concessions that we're going to make to tackle high dimensionality is that we impose structure. There are different ways to impose structure, and we are going to focus on two forms in particular. So take our linear model again. Suppose we do not want to impose any structure. Well, then we're basically screwed. There's not much we can do if we don't impose anything. Take p equal to n, then you basically have an x for every observation. So you can always fit the data perfectly, which is not particularly helpful. And well, this is a fundamental problem, right? So there's not, in that sense, not much we can do. So what we have to do is impose restrictions that, on the one hand, are meaningful, on the other hand, allow us to do estimation of these high-dimensional models. And what we are going to look at in this course is two ways to impose structures. One is called so-called sparsity, and the other is common factors. Roughly speaking, sparsity is going to impose restrictions on the beta. Common factors is going to impose restrictions on x. In its strict form, sparsity says beta is sparse if most of the components are close to zero. Actually, if we interpret it really strictly, it says most of the components are equal to zero. Now what it means, if the elements of beta are equal to zero, then it means that the corresponding variables are actually irrelevant for your outcome y. And that of course means you can do variable selection. You can try to kick out the variables that are not relevant from your model. And this is of course something we always do. And if we have something which is of, say, moderate dimensionality, at least too high than we want, we do, based on significance testing or whatever arguments, we do variable selection. Now, as I will explain in the follow-up lecture, variable selection, actually in its standard forms, right, there's nothing new about that, is not going to work if we have really high dimensions. It's going to work for smallish dimensions that are not small enough, but not for the kind of problems we want to deal with. Instead, what we're going to consider for that problem is what is called penalized regression. And penalized regression allows us to put restrictions on this beta. In fact, we can do more than just sparsity, so we can also put other kinds of restrictions on it, but we're going to put restrictions in a way that are often reasonable, but still allow us to do estimation and work in high dimensions, and in fact, in very high dimensions. And then in the second part of the course, we'll look at the alternative approach. So we look at the approach where we're going to focus on putting restrictions on x rather than on beta. And what we're going to do there, and that is often comes more from an economic point of view, is we're going to argue that many of the variables in here, the columns of x, are, informally you could say, they measure the same thing, or they are driven by common forces. So for instance, take a macroeconomic problem. You want to build a model to forecast GDP. And you have a bunch of explanatory variables that somehow measure the state of the economy. Now, all of these variables will be affected by the business cycle. How well is the economy doing? So something like the business cycle is a common force, or more formally a common factor, driving many of the variables in your x. I mean, and this you can apply in many settings. Think in finance, for instance, where if we would be looking at asset returns, we know that there are some risk factors that are driving these returns. Right? The most important one is, of course, the market return. So the idea of this approach is that we can extract these common factors from x. So we don't know a priori what they are. So here we have, of course, a market return you can calculate. But a business cycle already is much more difficult. But how do you measure a business cycle? We're often not even going to give them explicit names or interpretations, these factors, but we do believe that they are there and we can somehow extract them. And then in our regression model, instead of putting in all our x variables, we're just going to put in these extracted factors. Well, these are often will just be a few, and so you're actually back into a standard low-dimensional model. Then the third and final part of the course is going to deal with inference, where inference really means measuring uncertainty of your estimation. So we're estimating beta, we get point estimates. Those may come from, for instance, a penalized regression model, or those may come from a fractal model. But we want to measure uncertainty. So we want to do, for instance, do hypothesis tests or construct confidence intervals. And this seems standard, but in high dimensions there are lots of complications here. The first complication is that we typically do inference on many parameters at the same time. And that becomes a problem because, well, if you do a test with a significance level of 5%, you might argue, well, there's a type 1, the probability of making a type 1 error, so of doing an incorrect rejection is 5%. But that's on that's for a single test and not if you do it on 10 parameters. So clearly then the probability will increase. Now imagine you do it at 100 parameters, it will become much worse. Same goes for confidence intervals. This is the multiple testing problem, and we will spend a particular one tutorial working that out. What we will spend most of the time on in the lectures is the second problem, which is a much deeper problem and much more difficult to address. And that is that we do inference after we perform preliminary analysis. Now, this is not necessarily only a high-dimensional problem, it's a general problem in statistics, and we'll also take, in particular, at first, a general perspective on that. Right, so in particular, what we're doing is we're going to, well, take a very basic case, take your regression model. Suppose that your variable selection method works. You're first going to select the variables that are relevant in whatever way. Maybe you do penalized regression, maybe you do your favorite variable selection method that works. So you're going to, based on this model here, we're going to, based on the fit of towards y, we're going to choose regress as x. And once we do that, then in the second step, we estimate a model only with those relevant variables maybe. But we cannot really ignore that first step. So this is what, of course, typically is being done. People ignore the first step, which is a very bad practice because clearly you're already pushing towards those variables being relevant. Now, similar things happen in when you do first extract factors. You do first a step where you extract these factors from X, and then we put them in the second step. And can we actually do that as if they were observed variables? Now, in particular, so the same thing happens when you extract factors. What we do there is we first extract factors, and can we then include them in our regression models as if these were observed variables. Now, you can imagine if you do high-dimensional statistics, you do a lot more preliminary analysis, or at least with much more effects than in a standard setting. So even though it's already problematic in a standard setting, it's going to be much more problematic in high-dimensional statistics. Now, this is a field which has been thriving over the last years, and many people are working on this, and thankfully we have a bunch of solutions to these problems. And this will be the main material for the final part of the course.